It's going to have to warm up. If anything, it'll say warming up.
Hello and welcome to the very first episode of CNEN's new podcast, Stereochemistry. I'm Matt Davenport, and the person you just heard is Matt Hardings, a chemist at American University.
Not responding.
But we're actually at the National Institute of Standards and Technology, where Matt was on sabbatical this past fall. And you might already recognize the sound that you're hearing. It's the sound of research. It's the sound of something not working. Until.
There we are. It's working on it.
Oh, it's moving. We were standing over his 3D printer, waiting for it to start up. And it's just a regular 3D printer, you know, the kind that heats up plastic and then squeezes the polymer through a nozzle to build up one-of-a-kind plastic things. And I don't mean to downplay how cool regular 3D printers are. People have created all sorts of neat and important things with regular 3D printers. Things like models of molecules and proteins, things like cheap on-demand replacement parts for appliances, things like medical implants designed for specific patients. But at the end of the day, those things are still just plastic. And that's why we were with Matt Hardings in a lab at NIST. Although his printer is pretty standard, the materials that he prints are not. And we're here to find out why he's printing plastics laced with metal organic frameworks, or MOFs.
I have always been interested in 3D printing. There are all these stories of people who have 3D printed prosthetics and other amazing 3D printed things. But when I look at 3D printing, I do it from my position as a chemist. And I see these 3D printed things and I think, well, chemically they're pretty boring, right? You print them and they are chemically inert. They don't do anything else. And so I thought that, you know, as chemists, we're missing out on some of the fun in 3D printing. And so I wanted to find a way to 3D print things that did chemistry after they were 3D printed.
Enter metal organic frameworks. There are MOFs out there that can do all sorts of chemistry. There are some that are great for catalysis. Others can do gas sensing, storage, or separation. MOFs are a versatile and exciting platform for chemists. And that's what we're going to look at today in the first full episode of our podcast. MOFs are having a moment right now, and we wanted to really understand why that is. And honestly, I think the best answer that I have comes down to what might sound like a pretty boring word: stability. But I'm here to tell you that it's not boring. There is so much history and potential and just chemistry packed into that one little word. So we're going to spend the next half hour or so unpacking that excitement with some of the people making the most of MOFs. Which brings us back to that NIST lab with Matt Hardings. He's working with a MOF that's promising for storing hydrogen, an element that could provide us with a clean, sustainable fuel source. And Matt's team worked that MOF into a polymer composite, which the researchers can then heat up to like 200 degrees Celsius and 3D print into arbitrary shapes. For example, they printed these little perforated plastic towers that have oodles of surface area for gas storage. They also printed what looked like Lego bricks, and what scientist wouldn't be thrilled to get a box of chemically functionalized Legos for their birthday? But the idea is you've now got all sorts of flexibility to arrange MOFs how you want them. And MOFs come with their own inherent flexibility. And that will make a little more sense once I tell you what a MOF is. While reporting this story, I heard lots of amazing descriptions of MOFs. And this is not one of those. But it will work for now, and I promise you'll get a more complete picture of MOFs as this podcast goes on. So here goes. Imagine a sponge designed by the most anal retentive engineer in the universe. The sponge would not only optimize the amount of empty space it has, but it would do that by using the stable, ridiculously ordered framework around those empty pockets. And now, chemists have developed synthesis techniques that bring inorganic metal clusters together with organic linker molecules such that nature does the anal retentive engineering for them. Furthermore, chemists can tweak MOFs to get specific properties for specific applications, and they can do this by changing the MOF's organic chemistry, or its inorganic chemistry, or both. MOFs are a designer material that's now combined with the flexibility of 3D printing.
I can change the polymer that I'm using, I can change the MOF that I'm using, and I can also change the geometry that I print in. And I can change all of those things to go after different applications. If that application space is gas filtration, I'm going to print a different object than I would if I were trying to do gas storage and release. And so I can start to play around with structural geometry and printed geometry in a way that maybe I haven't been able to before as a chemist. I can start to see how these different geometries that I print in will facilitate the types of chemistry that I want to do.
There are just so many choices, so many options. I wonder if we know anyone who can describe what that feels like.
It's almost like a kid in a candy shop.
That's Omar Yagi, who is a professor at UC Berkeley and one of the founders of modern MOF chemistry. He actually just won a share of the Wolf Prize in chemistry for his MOF work. So who better than him to set the stage for us on how MOFs got to where they are today?
I sometimes say MOFs are the largest class of materials ever made by humans. And that's because you have exploited the periodic table of the elements, the transition metals, and the organics. And we figured out a way of linking those two together. When I got interested in this area, I was really interested in the beauty of these frameworks. I knew deep down that if you could stitch organics and inorganics together and make very stable frameworks, then you could apply all the beautiful molecular chemistry that has been developed over the last 100 years on materials, and therefore transforming not just the way you make materials, but the way you use materials. So what are the limitations on this? The limitation, in my opinion, is really our own thinking. For the first time in my career as a chemist, you can imagine a structure and go to the lab and make it. And when I was a student, if you imagine such a structure and went to the lab to try to make it, you got amorphous stuff that is uncharacterizable. And now we have figured out a way of making these as beautiful crystalline materials that can be characterized fully. We know where all the atoms are and we know how they're connected. And that's why the progress has been rapid.
Hearing this, MOFs blurred the distinction that I saw between molecules and materials. Chemists control which atoms or functional groups go where in a molecule to dictate its function. And that level of atomic control is necessary to design molecules. But not so much for bulk materials. For materials, researchers develop processing techniques that keep impurities or imperfections low enough to deliver the properties that they want, say mechanical strength or electrical conductivity. Or once they have an imperfect material, they can work on it with post-processing steps to improve the material's functionality. Now there are MOFs, which are ordered materials that you can basically synthesize from the bottom up, and fairly easily too. And let's actually take a closer look at one of the most famous MOFs, called MOF 5, to give you a better idea of what a MOF is. MOF 5 has a simple cubic crystal structure, or primitive cubic if you want to be technical and a little judgy about it. The crystal is a large cube made from smaller identical cubes with an atom at each vertex. The bonds between each atom make the edges. Fun fact, did you know that polonium is the only pure element with this crystal structure? That was news to me, so shout out to polonium. But I have a hard time imagining things I can't see. So for this exercise, imagine a cubic crystal structure made out of marshmallows and toothpicks. Just a giant cube made out of smaller cubes with a marshmallow at each vertex connected by toothpicks. The marshmallows then put the metal in metal organic framework. And the toothpicks are the organic part. In MOF language, the marshmallows would be the anchors or secondary building units. The toothpicks are the organic struts. In MOF 5, the anchors are octahedral zinc oxide clusters. And the struts are 1,4-benzo-dicarboxylic acid, which is basically a benzene ring with two stubby arms on either side to grab onto those zinc oxide anchors. Now, MOF 5 is a single, simple example of MOFs. There are more than 60,000 MOF structures according to one count from the Cambridge Crystallographic Data Center. And these MOFs can get way more complicated than MOF 5, like diabolically so. But even as a simple example, MOF 5 illustrates something shared by all MOFs. They're mostly empty space. There's not a lot of meat on those metal organic bones. Yet those bones are strong, and that makes today's MOFs pretty stable. That wasn't always the case.
Okay, so metal organic extended structures have been known for a long time. In fact, if you look in the literature, back in the late 50s, the Japanese were working already on copper-1 linked with an organic linker that has nitriles at the end of it that bind to the copper. And they made these extended frameworks. And many others following their footsteps have come up with similar structures, nitriles or bipyridine linked by copper or transition metal. When I came along, I started doing exactly the same thing. I took copper-1 and bipyridine struts, and we made these compounds. That was the early 90s, almost mid-90s. And you made these beautiful structures. And they were like sculptures. But very quickly we realized that they're not very useful because as we try to take advantage of the openness within these structures, the structures collapsed.
And good luck storing hydrogen in that, am I right? At any rate, it was obvious that these early frameworks were unstable, but Omar came to realize why. He tells us the bonds were to blame. The organic linkers they were first using, those nitriles and bipyridines, are neutral Lewis bases. This means that their interactions with transition metals are weak. So Omar and his colleagues wondered, what if they moved to a charged linker, something like a carboxylate?
So two things that the carboxylates gave us. One is that they gave us, instead of a transition metal neutral linker, now you have a transition metal with a charged linker. That's a much stronger bond than the nitriles and the bipyridines, but also the fact that these carboxylate came together and aggregated metal ions made metal oxide clusters as anchors. Instead of a single metal ion, now you have clusters, and these clusters are rigid and they are made entirely of strong bonds. So then we made the first, what we called metal organic framework.
In 1995, Omar and his team showed for the first time that they could move benzene molecules in and out of a MOF without the MOF falling apart. They then delivered another first in 1998 with a MOF they called MOF2. Using MOF2, they measured what's called a gas absorption isotherm. It's a measure of how much gas the MOF absorbs at a constant temperature under varying pressure. These experiments let Omar and his team figure out how much open space was available per gram of their MOF.
This experiment was critical because it allows you to get porosity parameters like surface area. And for the first time, we were able to compare MOFs to the more established porous materials. But the world didn't take notice of this development until we made MOF5 in 1999, because MOF5, that broke all records of porosity. We reported 2,900 meters square per gram. And that was a lot higher than people were able to obtain with zeolites, with mesoporous materials, and porous carbon.
So MOF2 was important. MOF5 set records. Are there any interesting stories about MOF3 or MOF4?
Well, MOF3 was the first MOF where we pointed out the importance of open metal sites.
If you think of a MOF's transition metal sites as inns or hotels for coordination chemistry, open metal sites have some vacancy or capacity left. They haven't filled up with organic ligands.
Open metal sites now are very important for separation of organic molecules and in enhancing the hydrogen uptake, methane uptake, carbon dioxide capture. So there's a lot of work that's being done at utilizing these open metal sites for those applications, but also for catalysis.
And I just realized he kind of dodged my question about MOF4. Man. Still, within their first 5 MOFs, Omar and his colleagues basically set the tone for the field. They put together these stable, versatile structures that could be chemically active and had massive amounts of storage space, and things took off from there.
You can get surface areas up to 7,000 meters square per gram. That is, in 1 gram of material, you have the footage of an entire football field. That is the space onto which gases can bind within the material.
When you say in 1 gram, there's the surface area of a football field, is that American football or the international football?
It's actually more than 1 football field, so either one would work. It's more than the soccer field or the American football field. In one of the MOFs, we called it the Queen of MOFs, MOF 177, had a porosity of about 5,000 meters square per gram. And we showed that, in fact, in a tank filled with MOF 177, you could store double the amount of hydrogen that you would store in a tank that does not have the MOF. And so even though the MOF was occupying volume, the MOF pores were acting to compact the gas molecules within the pores. And so this was amazing.
Omar and his team have already made more than 1,000 different MOFs. And I don't want to sound like I'm not impressed by that, but it sort of makes sense after learning how versatile MOFs are as a platform. You can change the metal anchors and the organic linkers and still do post-processing to get the functionality you want for a specific application. What does blow my mind, though, is that Omar wasn't really thinking about applications when he first got into MOF chemistry.
One CEO from Nalco Chemical Company came down to see what's going on about, MOFs were just beginning to be noticed by the community, and he wanted to see what is all the fuss about. So he came down. I was still assistant professor, and I was showing him all these beautiful structures and describing their intricate connectivities and their porosities. And then he, at the end of my little lecture that I was giving him, he said, "Well, what are they good for, Omar?" And I thought, here I am establishing a fundamental area of chemistry, and this is an intellectually stimulating world of beautiful new structures. And he's asking me how I could apply these to society. And I thought, I'm supposed to be a scholar, an intellectual that just produces knowledge and let society deal with it.
But the CEO then said something that changed everything for Omar. He flat out said Omar would never be a great professor until he brought MOFs to benefit society. And you can definitely see the impact of that conversation in the types of applications Omar's lab pursues. The group has built MOFs to store methane and hydrogen, to capture carbon dioxide, and even to harvest water. But other engineered nanomaterials, things like graphene and nanotubes, are also being studied for these applications. What sets MOFs apart? We'll get you an answer in just a second, but first, I wanted to thank you again for listening. We are so excited about this podcast and the fact that you're listening to it. We're also really excited about the stories we're going to tell here in the future, but we're going to be a monthly podcast after our first 3 episodes. So how can you stay up to date with the chemistry news you need to know?
They could subscribe to our newsletter.
Well, hello there, Senior Audience Engagement Editor Doria Reeser.
Hey, Matt.
Can you tell us a little bit more about the newsletter and how to get it?
Well, you can get our newsletter by opening your web browser and typing cenm.ag/CE newsletter. What can you get by signing up for our newsletter? Well, not only will you get the latest news, but sometimes we actually set up some special features, such as what's going on in policy or in the workplace for chemistry. You can also expect to see some really cool extra content, such as periodic graphics, which are in collaboration with Compound Interest, or Chemistry in Pictures, which features submissions from you guys.
Great, so can you remind us where we can sign up for the newsletter?
Absolutely. You can sign up for our newsletter at cenm.ag/CE newsletter.
And we'll also put a link to that in the episode description for you. So is there anything else we need to know?
Not about the newsletter, but I'm dying to know how MOFs are different from things like graphene and nanotubes.
With metal organic frameworks, there's this unique possibility and capability to synthesize them bottom up using chemical methods and very uniquely structured molecular building blocks. So from a synthetic chemistry perspective, there's a lot of modularity, creativity that can go into the design of these materials that gives them new emergent function compared to carbon nanotubes or other materials that have to be made and then functionalized.
You're probably wondering who that was.
My name is Catherine Mirica. I'm an assistant professor in the chemistry department at Dartmouth College.
Like Matt Hardings, whom we spoke with earlier, Catherine is also working to integrate MOFs with other materials, and moving to these sorts of composites feels like the next step in MOF evolution. 20 years ago, the question was, how do you make stable MOFs? Now chemists like Catherine are asking, how do you work with them? How do you process them? How can you weave them into the tapestry of materials we rely on every day? For Catherine's team, one of the ways is using electrically conductive MOFs with fabrics to make gas sensors and other devices.
Using the properties of the metal organic framework for what they're already known for in terms of porosity and filtration and capture. Using that in conjunction with electronic transduction, I think offers a lot of possibilities. Metal organic frameworks really offer very unique advantages in separations and storage of gases, as well as filtration and sensing. And I think the realization of that full potential really requires efficient, solid-state configurations of these materials and often composites with other materials.
Catherine then told me how she thinks about the MOF fabric composite as having this sort of hierarchical architecture, which is really hard for me to say out loud, but really fun to think about. MOFs have pores at the nanoscale, and fabrics are porous at the macroscale. Bringing these two levels of porosity together gave some interesting results.
Fabrics, we think, offer a very unique capability of porosity that can be integrated and harnessed in conjunction with the porosity of the metal organic frameworks. We actually see some really nice performance in terms of sensing, which we attribute to the dual porosity of the fabric and then being able to template the metal organic framework on top of that.
And I couldn't help myself. Anytime I talk to somebody about electronic materials and fabrics, I compulsively ask if they're making new wearable technology.
I think there are no reasons not to do that. We're definitely going in that direction. And I think this fabric-based platform is the first demonstration of the ability to integrate conductive MOFs into fabrics. MOFs have already been put onto fabrics. There's some beautiful precedent showing that, but they have not been conductive MOFs. And so being able to conformally coat fabrics and generate electronic textiles with metal organic frameworks, I think offers definitely some new possibilities for wearables.
As cool as I think it would be to wear MOFs around, the part of my conversation with Catherine that stuck with me the most was hearing her describe what she called emergent behaviors. In her case, that was seeing MOFs become better sensors when integrated with her fabrics. And many other researchers are working to explore these behaviors in other composites, for instance, by combining MOFs with glasses or polymers. And again, the idea is that a MOF composite delivers more performance than either the MOF or the matrix material alone. And that matrix material, the fabric, the glass, the polymer, could actually make up for some of MOF's shortcomings. I know, that's an about face after pulling the MOF bandwagon for this entire episode. But MOFs aren't perfect. For instance, when you synthesize MOFs, you typically end up with powder, and that's not great if you're trying to precisely engineer some sort of fancy device that uses MOFs. Here's Matt Hardings again.
It's difficult to just take a powder and throw it around and have it land on a device exactly the way you want it and have it stay in place, right? You want something where you can control the geometry, control the amount. You need to be able to have process control.
And although MOFs are more stable than their predecessors, remember, their predecessors were bad. So they're more stable than not stable, but that doesn't always mean stable.
You know, MOFs, while they are a really interesting class of materials, many of them are not stable in extreme conditions. Probably the prototypical MOF, which is MOF 5, will start to degrade at 60% humidity, right? And so that's not super extreme.
So Matt and his group did some experiments with 3D printing MOF 5. They wrote up a paper and they submitted it. And then they got reviews.
And we hadn't figured out that the humidity in our building at American University was, it's always at least 60%, right? 60% is the low threshold for where our humidity is. And DC is a swamp in general, and the epicenter of that swamp is American University. So it's always super humid, and our MOF was degrading before we put it through the 3D printing process. So I think that was, one of the biggest lessons that we needed to learn is how do we deal with humidity. The pieces that we have now, we can take them and plunge them into water for a week, and the MOFs inside of the polymers don't fall apart. So that's a big step forward in our eyes.
So just to reiterate, two of the reasons today's MOFs are remarkable are that they're porous and that they're stable. Now researchers are combining them with other materials that can add more porosity and more stability, and they can do this with materials we can already produce in process and mass. So the potential isn't just to create composites that are exciting, but ones that are also accessible. And I don't want to get ahead of myself. It's not like you can run out now and buy MOF Legos to build your own methane storage tank. It will be a while before that happens, if it ever happens. But this sort of material synergy helps explain why MOFs are having a moment. There's a lot of promise, both in terms of applications and the science to be learned.
I foresee us continuing to develop new ways to incorporate MOFs into larger materials, no matter what that material is, whether it's a polymer, things that I'm working with, or it's a fabric, or whether it's something else, right? How do we get those MOFs into a usable space? I think there's a lot of work to be done there. And so there's really interesting chemistry that'll make that happen.
That's the type of forward-looking quote that would be perfect to end a podcast with. But MOFs are having a moment right now. What kind of host would I be if I didn't tell you that MOFs are being commercialized right now? Well, actually, I'm not the best person to tell you that.
Hi, Matt. This is Omar from Northwestern. How are you?
In addition to being a MOF researcher at Northwestern University, Omar Farha is the co-founder and chief science officer of NewMat Technologies, which was one of CNN's 10 startups to watch in 2016. Last summer, NewMat partnered with Versum Materials to create gas cylinders with MOFs to store toxic gases used in the semiconductor industry. namely arsine, phosphine, and boron trifluoride. Using these MOF'd-up cylinders, semiconductor makers can store these hazardous gases below atmospheric pressure. That's safer than traditional gas cylinders that store gases above atmospheric pressure. Now, Omar concedes that developing toxic gas storage solutions represents a smaller market, but it's still a commercial market. So this answers some of the questions people have had about making MOFs at a commercial scale. And as has been the case with MOFs from the beginning, once you answer those fundamental questions, you build from there.
We already showed that MOFs can be scaled. You could go and make it that the price is competitive with other sorbents, and you could make it at a scale that you could handle a smaller market. Now, the next thing is go to the next markets, which they are larger, different storage applications or different separation applications. That it might require you knowing how to make the MOF even cheaper or forming the MOF with a specific formation. MOFs, when people started, you have to start somewhere and you have to show the world that you could build them by design and show porosity and show that you could make it and you could measure uptake and release of certain gases. And that was the main thing, let's say 20 years ago.
Fast forward to now?
We are really in the right time for the MOF, that you have materials that they are thermally stable, they are water stable, and some families are base stable, other families that they are acid stable. And these families of materials weren't there 20 years ago because the goal wasn't, let's worry about that type of stability. But now, because we have these materials, that allows us to go after the hard applications that 10 years ago we didn't have the materials to tackle. But right now, the MOF field has those materials, which to me is very exciting.
I asked Omar to check out the papers from Matt and Catherine's groups, showing how they worked different types of MOFs into different materials with different processing techniques. And he was really excited. But that got me thinking, is that Omar the Northwestern researcher talking? Or does startup co-founder Omar worry about these types of MOF materials making it out of the lab to potentially compete with NewMat?
To be honest with you, we are at NewMat, we don't think of other startups in the MOF field as competitors. We really do want more startups to show up, and we really do want more startups to succeed, because that's good for everybody, that's good for the field, that's good for the investors. It's a win-win for everybody. MOFs are a big platform, different startups going after different applications. They're not getting in each other's way. Is that going to be the case forever? Maybe not. But for now, I think the more MOF startups succeed, the better for everybody. And I think startups in general should be each other's cheerleaders and not think about each other as competitors. At least that's the way we see things at NewMat.
And hearing this took me right back to my interview with Omar Yaghi at UC Berkeley. MOF research had also taught him something about the importance of support in science.
So along each step, there was criticism and detractors. But the nice thing about the life of a scientist is that there's always some people out there that appreciate what you're doing. And they're not afraid to stand up and say, this is interesting work. This is worthwhile work. So I learned, now that I'm a senior professor, senior researcher, that whenever I see something nice that a young emerging scholar or an assistant professor, somebody starting out their career, when they are doing something truly groundbreaking, is to say, this is nice work. Keep going. And I was fortunate to have that. There were people out there, just like I had that CEO come into my office and propel me to take these materials to application. So this would be my advice for anybody doing research. It's research in itself is a very difficult endeavor because you fail a lot, and the reason you keep going is because of the potential success that you might get along the way. But during this process, you will have a lot of detractors. But don't forget that you will also have supporters, and that's what counts. The detractors, you have to listen to what they're saying because you have to address any weakness in your work that you might have. But there's always people out there who do make constructive contribution to your research by simply talking to you about the good and the bad in what you're doing.
So that's it. That's the real concluding quote of the first episode of Stereochemistry. We'd love to know what you thought of it. This is obviously early days for us, and we're going to experiment with telling different stories, different ways, and we'd love to know, like Omar Yagi said, the good and bad in what we're doing. You can tweet at me at Mr. Matt Davenport, and my co-host Carrie Jansen, whom you'll hear from next week, is at Absolute Carrie. Do not miss her episode. She's following up with the people behind CNN's cover story on sexual harassment to learn what's happened since the story came out. So subscribe to Stereochemistry now on iTunes, Google Play, or TuneIn, and leave us some feedback while you're at it. The music you heard first in this episode, and what you're hearing now, is What Have You Done by Lee Rosevere. And the music you heard during our chat with Doria Reeser about the newsletter was The Confrontation by Poddington Bear. We've got links to the songs and their licensing information in the episode description. For CNN, I'm Matt Davenport. Thanks for listening.